Hello, my name is Richard Conway from Telespazio. I'm pleased to introduce release 2.0 beta 2 of our EOEPCA project. First, for context, I'll provide a short background on the project and introduce the EOEPCA building blocks. Then I'll conclude by demonstrating our deployment guide. So the exploitation platform builds upon an infrastructure that already provides storage, data and compute capabilities. And really the role of the exploitation platform is to support extracting value from that data. So we can see this value chain in which the data is transformed typically through a number of steps, through analysis ready data, perhaps preparing data for machine learning, and then ultimately from that data through processing you can extract information that is then can be presented to decision makers. And so within that chain there are a number of capabilities that are needed. So the data needs to be discovered and it needs to be retrievable or visualizable. Then there are various layers of processing. So you need a capability through which platform users can express their own processing algorithms. Then the data can be transformed, for example, into data cubes to make it more easy to analyze in the higher layers of the platform. And also there are considerations for machine learning as well. So the ability to prepare data and to perform machine learning on it. Ultimately, to make that data available to decision makers and users, we can envisage the use of dashboards and also clients that interface and make the data more consumable by users. So there are many such platforms, data platforms, processing platforms, and the problem that has arisen as a consequence of that is, and now there are many platforms, but the ecosystem is quite fragmented, such that it's not easy for users to use the offerings of those platforms in combination. You know, often they're quite complementary, and what we're trying to do is to facilitate that. So what is our approach of the common architecture? So it's to first of all encourage that the federation amongst platforms by using open standards, and also promoting standards for interoperability as well. Through that we have defined an architecture that's based around what we call building blocks, each building block representing a certain capability within the platform. And then building on that architecture, we have also built a reference implementation of that architecture, which comprises a number of open source components which are designed to be reusable. So these are reusable building blocks. And the motivations there are to avoid fragmentation, but also to facilitate platform providers with a ready-made solution, and so to reduce development costs. So the project is now in its phase 2. So phase 1 concluded with in February 2024 with our last formal release, which was version 1.4, and we are now in this second phase, phase 2. So we're very much working towards our 2.0 release. Between those two phases, at the end of phase 1, we took the opportunity to reappraise, to take a critical look at the architecture and to assess whether we needed to refresh those building blocks, perhaps with a different implementation, or indeed to augment the building blocks that we already had with additional capabilities. So as part of that process, we now have a new, since 2024, we have a new set of providers and an ongoing and increasing set of building blocks within the project. So in terms of the architecture, just a very quick overview. You can see with the diagram on the right, there are quite a number of building blocks, quite a number of capabilities within the platform. And this is this is what's in the architecture, and this is what's reflected in our reference implementation. Just to clarify, what actually do we mean by the term building block, which comes up a lot in our documentation. So building block is a software component that implements a specific platform capability. So typically it's got a REST API, and generally where there was a standard available that met that capability, then we've tried to use that standard. We target Kubernetes for our reference implementation, so each building block has one or more Helm charts through which it's deployed, and they are all so we have a system, so we offer up a set of building blocks as an integratable set of capabilities to form the bulk of what you might expect in a platform. But equally, they are designed so that you can pick and choose and just pick particular capabilities if that meets your needs. And of course, all of this is open source. Our approach also is community oriented. So we are very much open to engagement, either to help us define the capabilities that are needed, the use cases, or to help us design or develop those building blocks, or just to be an adopter of our work. And as part of that, we are engaging now with the OSGO, so we've recently become a community project. And we also, a lot of the standards we use are OGC standards, and so we also engage with OGC working groups and test beds. So I'll quickly walk through the building blocks that we have, which are at different levels of maturity, as we'll see as we go through. So the first broad area of capability is around processing. So we have two approaches here. We have one that uses OGC API processes, which is suited to what we would say general purpose processing. And the reason for that is it allows user-defined processing in which workflows can be containerized. So any existing algorithms, for example, in any languages, as long as they can be containerized, then they can be packaged using this OGC application package, and they can then be submitted to the platform via this interface and via this building block for execution as a processing job. On the other side, we also now have OpenEO, which provides an API and a set of clients that allow you to perform a more client-oriented semantics. So, driven from your processing, your programming environment. So typically Python, R, JavaScript clients, and the semantics of that API through those language bindings have very close integration with the data that is being operated on. We also have support for different runners in the back end. So right now we have focused on Kubernetes, so the execution of those workflows within Kubernetes. But we also have some ongoing work to introduce backends that interface instead for execution of the processing workflows within HPC, and also support for Dask. Okay, so another set of building blocks around management of resources. So first instant discovery of resources. So we have a resource discovery building block. That it's not just data, it's all sorts of resources that are relevant within the environment of an exploitation platform. So that's data sets, of course, but also the workflows, Jupyter notebooks, machine learning models, and training data, and even resources around source code repositories for processing algorithms, for example, and associated documentation. On the data side, so we have a dedicated data access component, That also includes a discovery service through Stack. But that's offering, that's making the data available for retrieval and visualization through these standard interfaces. So the OGC interfaces for features, maps, and coverages, for example. For analysis ready data, this is coming soon. So we have a data cube access building block, which is providing a specific API for accessing multi-dimensional data. And so that is really to try and consolidate the access and manipulation of that data into a single API. Linked to resource discovery and to data access, we have ingestion and harvesting through the resource registration building block. So this provides both an API for submitting new records into those services, but also a workflow service that allows routine harvesting of data from external sources. The workspace provides an environment for users of a platform where they are able to manage their own resources within a platform. So, for example, they're able to have their own storage space and associated services to that. So, for example, they can upload data of their own, for example, as input to processing. They can perform processing in the platform, and all of the outputs of that processing can be located within their workspace. So it provides that context, if you like, for their work within the platform. And it also is designed for integration with the other building blocks within the system. So, for example, integration with processing for storage of results. Okay, so moving on to more sort of user-led analysis and exploitation. So we've got a set of building blocks here around this. So the machine learning, the MLOps building block is supporting the workflow to manage machine learning model training, management of the data, training data, management of the process of training, and then of the model assets that are produced through that process. Then for interactive analysis, we have a service, the application hub building block, that is based around Jupyter Hub. So not only does it provide Jupyter notebooks that are integrated with the services of the platform for data analysis, but also we have an approach that builds upon that to allow the creation of dashboards that can be containerized, and they can then be used to showcase the outcomes of research, for example. So where a project has maybe produced some research outcomes, they can be showcased through interactive dashboards. The application quality building block. So this is providing tooling during development of applications. So applications will typically be the research that's taking place. So development of algorithms, for example, to derive value from the data. And this is really providing an environment that encourages best practice around how they are developed. So it's tooling for static analysis of the code, but also ensuring that the approach taken by the project is following best practice for open science, including provision of documentation and things like that. And then in addition to that, some tooling to support testing and tuning of the performance. So it's really designed to improve the quality in the end of what's produced. The notification and automation building block. So that is to provide event-driven behavior within the platform and amongst the building blocks. So the idea being that building blocks can produce events that can then be triggers for automated behavior in the platform. So, for example, you could configure systematic processing linked to data within a given data set, for example. And then finally, the resource health building block, which is really designed to support projects who have produced some added value outcomes within the platform, and they are publishing those for consumption by others. And what the resource health building block allows them to do is to define automated monitoring and associated alerts around the availability or the performance of those resources. So that could be data sets, workflows, or applications that they have published as outcome of their work. And finally, the final set of building blocks, federated orchestrator and data gateway building block. They're not included in this release, but they are coming soon, and they're defined within the architecture. So the federated orchestrator is concerns execution of workflows, processing workflows that span across more than one platform, and also potentially span across the different processing approaches that I mentioned earlier. So the ability to combine steps of a workflow that are designed around API processes and combined within the same workflow steps that utilize OpenEO process graphs, and all of that being executed and distributed across more than one platform. The data gateway building block, that supports federation by providing an abstraction, a programmatic abstraction of data that's available in, again, a variety of different providers in different platforms. So if we can abstract the semantic of accessing that data, it makes it much easier for users to employ workflows that work across multiple platforms. And that abstraction takes away the complexities that maybe exist with different protocols being used by the data providers, or their approach to authorization and authentication. The abstraction therefore smooths out, it reduces the friction for the users accessing those data sources. And then finally, across all of the platform, the use of federated identity and identity and access management. So we have a building block for this, which is designed to support single sign-on, designed to integrate with different external identity providers, and it's designed to provide a consistent approach to the protection of access protection to building blocks. So that was all the building blocks. You can see them all again here. These are our partner organizations. So Telespazio are working with ESA to provide a system level overview of the project. And then we have different expert teams, as you can see here, the logos, many different partners with different responsibilities for the different building blocks that I've presented here. Our documentation, so the project uses Read the Docs to provide its documentation. So we have the top level EOEPCA documentation set that you can see on the left hand side here. And there is technical documentation, but also tutorials and other learning materials such as how-to guides. Included within that, we have a system architecture that defines a high-level architecture that supports the reference implementation. And then we have documentation for each of the building blocks. A specifically important document in terms of the release is the deployment guide. So that's available here. So what I'm now going to do is move on to introducing the release just by introducing the deployment guide. I won't go through the whole thing. I'm just going to sort of provide an example of a small number of building blocks just to illustrate the approach that we take to the deployment. So the deployment guide splits broadly into two parts. The building block deployment itself, where we go through each of the building blocks in turn and describe how each of those are deployed. But before that, there are some prerequisites. So we'll go through those to make sure that not only do you have a Kubernetes cluster, but it satisfies some of the dependencies that are assumed by the deployment of those building blocks. So in terms of the high-level prerequisites, so you need a Kubernetes cluster, and we assume also that certainly in the way we present the guide that you're able to establish some sort of DNS to route traffic externally to that cluster. I'll go through the requirements just to point out, we'll come back to here actually, but we do have a number of scripts that support the deployment. So one of them here is to check that these prerequisites that are mentioned here are met. But first, let's go through the prerequisites and see where that takes us. So first of all, you need a Kubernetes cluster. You need an Ingress controller, which acts as the reverse proxy for the to take the traffic into the platform. And ideally, that's combined with a wildcard DNS, which allows each of the building blocks to use host-based routing for ingress of their traffic for the different services of the building blocks. There is also a requirement at the minute. Some of the building blocks have an expectation that containers can run as root. And in terms of getting traffic into your platform, we might expect there to be some sort of a load balancer that is offering the public listening on your public IP address and is routing traffic on the typical HTTP ports into the platform, into the cluster. And again, we advocate the use of Cert Manager, typically configured with Let's Encrypt, in order to obtain certificates for your platform. But there are other pathways here that are mentioned in the document. So as a quick start, and also what we use to support development and testing. So in our development environment, we have a cluster with 6 nodes, I think. For that, we're using the Rancher Kubernetes engine. If you are just looking to evaluate EOEPCA and you just want to do something very quickly, perhaps even locally on your machine, then what I'm going to do here is follow this quick start that uses K3D, which is another product from Rancher, which allows you to create a single node local cluster on your own platform. So I'm going to follow this guide here now, and we'll do this together. So first things first, if I can find it. Here we go. So the first thing to do is to clone the repository. So I'm going to just take this command here, open a terminal, and okay, And then I'm going to clone the repository. So we're using this 2.0 beta branch of the repository. And then we'll open that up. So if we now jump back to the Kubernetes quick start. So this is the K3D cluster create command. What I'm actually going to use, there's a variant of this that allows me to specify my Docker Hub credentials. And that can be useful if you have experiencing issues with rate limits on pulling images. It helps to have an authenticated account there. So there's an extra argument basically at the end that defines the registry information. If I copy that into my environment, and I'll copy that locally, and then so this is instantiating a Kubernetes cluster. I'll just jump back to the guide. What I'm doing here is I'm exposing these ports here into the cluster. So 3.1.0.80 and 3.1.4.4.3, and that reflects the fact that my external routing for my external IP address is forwarding through ports 80 and port 443 onto those ports. So this will bring in the external traffic. Of course, for your environment, you would need to adjust that to how you have your network configured. What I'm going to use during the guide, I'm going to use a tool called, so we can use kubectl. To interface with the cluster. The kube config is defined, so this is was output by K3D, the K3D create command. So that's given me a local kube config, and I've got my kube config environment variable pointing towards that. I'm going to use a tool called K9S, which during this guide, which will provide, I think, an easier way of visualizing what's happening in the cluster. Okay, so the cluster is running. There's a few pods representing the core services. So moving along, so storage requirements. So you need to define a storage class within your cluster to support dynamic creation of persistent volumes used by many of the building blocks. There is currently a requirement, mostly coming from the processing building block, for a storage class that supports read-write many volumes. The processing solution has the ability to take a workflow, and depending on the workflow, it's able to parallelize the execution of that across multiple nodes using a scatter pattern. And the approach that it takes relies upon some sort of distributed storage, some shared storage that allows the splitting of that task across multiple nodes. And therefore there is a requirement, at least for the processing building block, for this read-write many storage class to be available. So again, as a quick start, if you just want to do something for development purposes, very much not for production, what we can do is we can apply a simple host-only storage class that does indeed support read-write many volumes, but that will only work for a single node cluster, so it's very much only for development, but it allows us to progress. Otherwise, for a production cluster, There are different solutions as described in the guide through which you can provision some sort of distributed storing, NFS maybe, or capabilities such as Longhorn or Gluster maybe are also suitable. So I'm going to just copy the deployment YAML for this storage provision, host pass storage provisioner. Okay, we can then jump back to the cluster, and if I list, I can now see that we've added this standard storage class in addition to the one that's built in to the K3D deployment. Okay, so that's the cluster and storage, and then we also need an ingress controller. So for our IAM solution, we have an expectation that the API 6 ingress controller is used. Again, as a quick start, we're going to deploy that. For a public-facing cluster, at least, you need some sort of a dynamic DNS to allow the host path routing that is configured in the ingress for many of the building blocks. For testing purposes, if you are just working locally, you can use a service like NIP.io, which will just you can just use an IP-based local DNS effectively for that. So in terms of what I'm going to use here, I have a domain. So if I run this command here, so I'm going to use this domain test.eoepca.org, which routes through to my IP address on this platform, and we have wildcard on this, so anything within that domain will map through to this IP address. Okay, so we're going to deploy the API 6 ingress controller. This command here again is configures the values of the Helm chart appropriate to the environment that is being walked through in this guide. So again, we see these node ports that are upon which the ingress controller will listen, and that matches the ports that are exposed by my cluster. So I can just copy and deploy using the Helm chart. And okay, so then if we jump back here, we can take a look at the pods. Of course, it takes a little while to pull the images and load the pods. While that's carrying on, we can just look a little further in the guide. So what you get with API 6 is you get some custom resources as well. So and we can use those right now to configure certain aspects of that ingress service. So the first one is we can use this, what it calls a global rule, to enable redirection to TLS, with a few exceptions here. So again, we can copy that, and we can apply that. Okay, so that's been created. I will just restart in order for K9S to reload those CRDs. I'm just going to restart it, and then we can just double check. Okay, so we can see that that has been well applied. So back in the guide, there is a further global rule that we wish to apply. And this is to do with some behavior that we've seen within API 6 when its container port is not running on 443, running on in this case a higher numbered port, 9443. Then we apply this global rule to fix the way it reports that published port when it's forwarded, applying headers for its forwarding. So you can copy that, paste it, and then that gives us this second global rule. Okay, so that's the Ingress controller, then TLS. So what we're going to do here is we're going to deploy Cert Manager in order to, and we'll configure that to obtain certificates via Let's Encrypt. Okay, so we talked already about the need for the wildcard DNS, and first we deploy Cert Manager here. Okay, so while that's installing, we can check that the pods are running, and that completes. So now that's running, we can configure a cluster issue. So there's a couple of choices here. There's different ways that the challenge can be presented, either by HTTP, or if your DNS provider supports it, then you can use the DNS challenge instead. For the DNS challenge, that has to be configured for your particular provider. So this example here shows you use of Cloudflare. For now, we'll just use the HTTP challenge, which relies upon Ingress. The challenge comes back into your platform to prove that you own the domain. And so we've configured this with the Ingress class that we're using, which is API 6. And we give it this name here. So I'll copy that, paste it in the terminal, and then I will edit the email address. Okay, so that creates cluster issuer. Again, it's always worth checking. Okay, so again, when new CRDs are loaded, you have to restart K9S. There we go. Okay, so that's done. So the final prerequisite we're going to do here is to deploy Minio to give us some object storage. So some of the building blocks expect to be configured with object storage for managing their resources. And of course, depending on which what your environment is, you may have the ability to integrate with prevailing S3 object storage within your cloud. But it's convenient here for us to deploy Minio, which we can then rely upon to configure against the building blocks. I guess what's also worth mentioning at this point is the deployment of Minio follows the same scripted deployment approach which we introduce for all of the building blocks. So if I just follow the link here, I can perhaps describe this. So each of the building blocks is deployed by one or more Helm charts. But in order to customize those charts for your environment, then you need to configure the values for those Helm charts, and the values, you know, for Helm charts can often be quite complex. So in order to simplify that, in particular, if you're looking for a quick start, we have some scripts that do a number of things. They help to generate the values files by asking you some questions via the scripts, which allows you to describe the details of your particular deployment. And then it uses those values to populate some templates we have for the values, which are then used to deploy the Helm charts. Of course, these are only there as an aid. That doesn't really, and maybe even as a starting point. So we generate a values file that you can apply, use to apply with the Helm chart, but you can perhaps see that as a starting point, and then you can adapt that even further according to the deployment needs of your cluster. And the other advantage of this approach in terms of the values files is it means that when we are deploying multiple building blocks, then we are configuring them consistently, because the values that are configured in the scripts are shared, and so we're making sure we're using the same values. Beyond the values, the scripts actually, the approach for the building blocks is the same. So we have a script that allows you to check the prerequisites for each building block, and each building block maybe has different prerequisites that are expected. So we're able to use these scripts to first check that. Then we can configure the building block with the values, which supports the deployment via the Helm chart. At the conclusion of the deployment, then we have a script that you can run to perform validation that the deployment has completed as would be expected. And the scripts themselves, in particular the configuration script, uses has some sort of state management. So it stores the state that you're describing of your environment in this state file, and that is then used for the deployment of subsequent building blocks. As I said, this then aids the consistency of the deployment across the building blocks. So this is a common approach. So the first case here is for Minio. So it describes the building blocks. So now what we can do is we can jump straight in and run the check prerequisite script for Minio. So, well, I guess this repeats each time. Of course, you don't need to keep cloning the repo, but it's belt and braces, I guess. So what we're going to do is we're going to change into this script's Minio directory, and then we're going to run this script. So I'll copy that. We're going to change to script Minio, and then we can check prerequisites. Okay, so first time through, we'll get the questions that are pertinent to this particular building block. So in this case, we're going to stick with the default HTTPS. And it's done a number of checks. It's checked, first of all, that we can reach the cluster, that we've got kubectl, we've got Helm. These are tools that are relied upon. Cert manager, we know we've installed the Ingress controller. So at that point, it's happy that Minio, the prerequisites are met for Minio. So then we can move on to this configure step. So I've copied that, run this, and we get some more questions. So the base domain in my case is test.eoepca.org. Kubernetes class for persistent volumes. So in your case, you would have to decide what storage class you have configured within or is available within your cluster. For us, we have this in our development setup here. We have this standard class that uses the host path provisioner. So we can go with the default. We're going to use Cert Manager. cluster issuer, so we set this up earlier, so again it's defaulting to the value that we configured earlier. Okay, so a number of things have happened at this point. First of all, the state file that I mentioned has been created, and the questions that we have answered have been recorded in this file for future reference, plus some extra derived parameters as well. The other thing that's happened is, if we tunnel into where we were, so we're in scripts Minio, we ran the configure Minio script, and what that did was it used a values template file. So here we have the values template, and you'll notice it's got some substitution values in here. So it used this template to generate the actual values that we're going to apply to the deployment itself. So you can see the values have been completed in accordance with, for example, my domain. And that's really an illustration of the general approach that is taken with this scripted deployment across all of the building blocks. So jumping back, so we've run the configuration. So now we can apply the Helm chart, and you'll notice that the values it's using are the generated values. So I'll copy that. And this should now deploy Minio. Okay, while we wait, we can maybe list the pods. You can see the Minio pods are now running. Okay, the Helm chart deployment is complete. There's an additional script in this particular case, which is applying some secrets into the cluster based upon with the credentials of the Minio user. So we can run that script. So this is asking us for the S3 access key, which is explained here. Okay, so I've missed a step here. So first thing we need to do first is create an access key and secret, which is what we're going to apply here into the cluster. So let's just grab the URL, put that there. Okay, so in order to log in, we first need the credentials that are in this file. So of course, to support this scripted deployment, we're maintaining this state file, which has various sets of credentials in it. This is really just an aid to support the this demonstration deployment. You know, in general, keeping your credentials in a file like this isn't such a good idea. But the idea of this guide is to facilitate you to understand how to deploy the building blocks, and then you can build in your own credential management approach around that. So for Minio to log in, we've got the user, and here is the password that was generated by the configuration script. So I can copy that, I can jump back here and log in. Okay, and we immediately notice that again, this is according to the values that was in the values template. We actually specified a number of buckets to be pre-created, ones that we know will be anticipated by the building blocks. Okay, so now we've logged in as the default administration user. what we're going to do is we're going to create a new access key that we're going to then store in the secret. Okay, so create an access key. Any details? So all we need to do now is copy that and go to the, so we're back to the apply secret script here. So that's the access key. And we can grab the secret. In fact, I should probably hit the create button here. Okay, so I can copy it from here. Paste that in. So two things have happened there. First of all, again, it's dumped them in this state file. But it's also, I think, yes, it's created this secret also in the cluster. Okay, so that's that done. So we can run this validation script, making sure we're in the right directory, which is this Minio directory. And this is just doing some custom checks for the various pods and services and volumes that might be expected. And it's also tested some of the expected endpoints as well. So we can follow through some of these checks. You could do, there are some manual checks that you can do here. We've seen this, we've logged in, we've seen these buckets, and you could do some manual checks yourselves via the interface. Okay, so skipping over container registry. So if we jump to the application deployment, so now these are all the building blocks. So I'm not going to go through all of these, but what I am going to do is I'm going to deploy the IAM building block, the resource discovery building block, and the processing, the OGC API processes building block. And once I've done that, we can demonstrate the outcome there by protecting the OGC API processes endpoint with the IAM, and we can execute some processing and see the outputs arrive into a bucket within Minio. Okay, so IAM, what we'll see now is a similar approach to what we've seen from Minio for deploying the IAM solution, which is based around Keycloak and OPA. Okay, so I'll copy the script. In fact, I've jumped ahead slightly here. So if we go back to the validation script, it's asking us if we want to proceed with the Minio functionality tests, which I hadn't noticed. So we can say yes to this. And what it's done here is it's done a series of steps. So it's created a bucket, it's uploaded a test file, it's done a listing, so we can see that the test file is indeed in the bucket. It's then deleting it, and then it's deleting the bucket, and all of that has completed successfully. So that's a useful sanity check on that deployment. So back to the IAM, if I change directories into IAM and I run the check prerequisites, again, similar checks to before, they're all satisfied. Then moving on, so what we're going to do here is we're going to deploy Keycloak, make some configuration within Keycloak, in particular in EOEPCA realm, and deploy OPA as well. So as before, we've got a configuration step. So any question that we've already been asked, because we have the state file, we already have the answer to that. It offers us the chance to change it, but if we just hit return, then it will accept the value we already have. So these are all good. Okay. And as before, what's happened there is it's generated not only a values file in this case, as before, so we've got the Helm values file, we've also got an ingress has been generated, again from a template, in particular filling in, for example, the domain that we expect. It will be apparent what we do with that in a sec. So if we jump back to the document, we've done the configuration step. We already have API 6 installed, so we can carry on. There's an apply secret step here, so we can do that. And there's various secrets that were generated during the configuration step that have now been applied as Kubernetes secrets into the cluster, as expected by the different services. And now we can move on to deploying Keycloak. So again, we copy the Helm command, noting that it's using the generated values for Keycloak in this case. And we can just double check that everything looks healthy. Takes a little while. While that's running, we can just jump back here and check what the document says. So the next step, we need to wait until it's up and running, but the next step will be to run some commands here that will use the Keycloak API using curl to automate creation of the EOEPCA realm. So we just need to wait until the deployment completes. In fact, while we wait, I realise there is a step I've missed. So we've already done the Helm command to deploy Keycloak, but what we haven't done is apply the ingress. So again, there's one of these files that's been generated from a template. We can copy that and we can apply that. And that creates 3 objects, and this is typical of Ingress with API 6. There's the API 6 root that defines, in fact we can look at it here. There's the API 6 root that defines the reverse proxy into the Keycloak service using this host name. And then in support of TLS, there is a certificate that gets generated via Let's Encrypt using the cluster issuer, and then we configure that against this host within API 6 using the secret here that is generated as part of this certificate. So that's fairly typical of Ingress, a simple case of Ingress. Okay, if we jump back to this view, okay, so now we can see all the pods are running. So we jump to the dock and scroll on, we can see that we can copy that, and we are going to use that to Okay, not a lot of feedback there, but two things happened there. First, we made a call to get an access token using as the admin user within Keycloak, and then we used that in a call to create this new realm called EOEPCA. And the substitution values were supported by the fact that we've sourced that state file here, so that it's able to substitute the right values in for our deployment. And now we can, there's a supporting script here. So what we're going to do is to support some of the other building blocks, to demonstrate some of the other building blocks, we're going to create a user that we call EOEPCA user in this new realm. So, okay, copy the script. So this is the details for the admin user. These should already be set, so we just hit return on those. The full host domain included, right? Okay, surprised that the default wasn't better, but I can type that in. The realm is EOEPCA. Okay, so the username, so I'm going to go with the default here, this EOEPCA username, and same for the password, nice and simple. Okay, so that has, again, it's used the Keycloak API underneath this script, create user script, to create a user for us. And it's probably worth checking that. So if we, no, in fact, if we, okay, so we list API 6 routes. So we saw the ingress that we created via an API 6 route. So we can just grab the host name. We can log into Keycloak, and in terms of credentials, we can consult this state. Keycloak admin user is admin password here. Okay, so we can log in. We can see that we have indeed got the EOEPCA realm, and if we check users, we can see that we have EOEPCA user. Okay. There are some optional steps here. I won't go through them now. For example, to add GitHub as an IDP integrated in Keycloak, so you can follow those steps. Right, so moving on to OPA. What we first need to do to support OPA is to create a client within Keycloak for it. So we have a helper script for this, so we can run the create client script. Yeah, these are all defaults. Okay, so now we get on to some questions. So we're going to call this client OPA, and I'll grab this text here. So client ID is important because it's referenced, it will be referenced elsewhere in other configurations. So we're calling that OPA. The name is more a display name. Again, I'll just reuse that, and then something slightly more descriptive. Okay, enter the client secret. So the client secret has been generated by the configuration script, and therefore it's in this state file. So what I'm going to do in a different terminal, cat that state file. So we can see here the OPA client secret is this one. So this is what we're going to set into that client as we create it. Okay, so the sub is asking for subdomains, and that is in order to configure the redirect URLs that are applicable to this particular service. So in the case of this service, we have just a single subdomain OPA. Just type that in, and then there are no additional subdomains needed in this particular case. Okay, so that's been done. We can jump back to Keycloak and look at clients, and we can see it's been created. Of course, this can all be done in the UI of Keycloak. The helper scripts are really just there to keep things simple and to aid setup, particularly if you're looking for a bit of a quick start. Okay, so moving on swiftly, following similar steps. So we've got this Helm command to deploy OPA. So we can apply that. List the pods. Okay, we can see those are emerging. Back to the document, we can, while we wait, apply the ingress. Close that terminal, apply the ingress. Similarly to before. So now we've got routes for OPA. Just wait now while they finish deployment. And what we can do while we wait, we can always inspect. So using K9S, we can inspect, describe as it calls it, and we jump to the bottom. You can see events this is useful for debugging in the case that something's not working. Okay, so now that's running. We can progress to run the validation. Okay, validation. And as before, it's doing lots of checks, just that things are meeting expectations per pods, services, and endpoints typically. Okay, so that's there's lots of checks here that you can perform by hand. Just scrolling through it now to check there's nothing we need to worry about. At which point we can carry on. So the next building block I'm going to do is resource discovery. So we jump ahead to that. So resource discovery comprises, in this case, we're going to be deploying the resource catalog. So again, it's got a set of prerequisites. It's very similar to before now. You start to sort of recognize the approach. I'll copy the script. I'll change directory into resource discovery. And I'll run that check. Okay, everything's good. I'll run the configuration script. Again, we work through the questions. Many of the, as you go on, the answers are increasingly already answered for you. So as before, we've got 2 files have been generated, the Helm values and the ingress to apply as before. So we can proceed to run the Helm command. Okay. And we can already see the pods are deploying. While we wait, we may as well also apply the ingress. Okay, takes a little while. Okay, it gets there in the end. So now everything's running. Okay, so we can run our validation script. And similar checks to before, all passing. And then we move on. There's some sort of manual validations we can do here. So we can, for example, jump to the landing page, filling in our domain. Okay, so this shows us the resource catalog. Okay, we can see collections. We've got no records. I guess we can see there's a Swagger endpoint. We can jump there, see that the Swagger endpoint is running. Yeah, conformance. So we can just manually run these checks. Just scanning through a bit. I guess we can maybe run. I mean, we've got no records, so we're not going to get any results, but we can at least check the endpoint, and we get back a result with, you know, a well-formed but empty answer returned. Just trying to, maybe we can, yeah, visualize that slightly better so we can see we get a good answer back. We can introduce a record, just a sample record. So what we can do is slightly manual steps, but we list the pods. We grab the pod name, and what's it telling us to do? So we're going to copy a test file into that pod. So like so. This is a sample record, so that's copied into the pod. And then we are going to invoke a command in the pod. So first we're going to connect. Like I said, fairly manual set of steps. So now we've got a shell within the pod. We can run this command to load that record. Okay. And then if we jump back to the catalog and we go into the items, we can now see that we've got a sample record. Okay, so that's it for resource discovery. So the final part of the demonstration is to deploy the OGC API processes engine, as we call it. Okay, so similar to before, we copy the check script, we change into the, oops, no, not that one. In fact, an additional subdirectory, we can now run the check script. Everything works. We run the configuration script. Okay, usual questions. Okay, so this is where it gets slightly more interesting. So the question it's asking us here for the processing is it uses a node selector to choose which nodes processing workflows get scheduled on using labels on those nodes. So there's a default value here, kubernetes.io/os as a label. So this is an opportunity for you at deployment time to perhaps configure within a proper cluster, not a single node development cluster, a set of nodes that are maybe labeled for processing, for example. So it's an opportunity to do that. In our case, we're on a single node development cluster. We only have one node. If I describe that, I can see the labels it has, and I can see that it does indeed have a label, this OS label with a value of Linux. So at this stage, for this demonstration, I just need to make sure that I've got a matching label. So this one is going to work for us. So if I jump back to here, I can accept the default for the key, and again for the value, the default value of Linux, it matches the label I have for my node. Okay, so in terms of the processing building block, it integrates with object storage, both for staging data in, input data, and also for staging data out, where to push processing results. So in our case, we're going to rely upon the Minio instance. So this is the URL for the Minio API. And we rely on the values for the access key and secret that we configured earlier and stored in our state file. Region, default region, I'm not sure it matters so much for Minio. And then it's asking us whether we want to configure an alternative store, alternative S3 endpoint for the outputs. In our case, no, we're just going to rely upon Minio. Authentication, yes, we're going to use authentication. In order to support authentication, i.e. protection of the endpoint for the processing service, we will need to configure a client within Keycloak. So the name we will give to that is this OAPIP engine. So that's the default, and it's generated a secret for us, which as usual is put in that state file, and we'll need that shortly. Okay, so having completed the configuration, all of this is of course described better in the page of the guide. So first thing, we will deploy the processing service. So it's provided by the Zoo project. So we copy the Helm command using the generated values. That should deploy the service. So we list the pods. We can see the pods kicking off. Okay, so whilst that's deploying, in parallel, what we can do is we can create the client that we just configured. But we configured the credentials for, but we need to actually create the client itself within Keycloak, so we can use the helper script as before. Whoops. So, usual questions as before. Okay, so now we get to the client ID, which has to match what we've configured within, or will configure within the service. So this is the client ID. So we'll copy that. That's your client ID. The name for the client, I think that matters less. I'll reuse that, and then it's useful to put something descriptive here for that. Okay, so for the client secret, I guess we can see it here actually, but that should also match what's in the state file. Okay, so we've got the client ID that we saw here, and then we've got the secret. So we can copy that, and we can paste that in there. Okay, so for the subdomains, so again, this is for redirect URLs. We're just going to use Zoo because that's the host name that is used by that service. So we haven't got any additional. Okay, so that's created that client. If we jump back here, we can see that all the pods are now running in the processing namespace, so we can carry on. Okay, so in order to protect the resource, so we're going to move on to the script here. In order to protect the resource, we need to have a user that will have access to that resource. So it's telling us to if we need to run the create user script, we ran that earlier. We already have this EOEPCA user, so we can jump straight down to running this protect. So what we're going to do here, just by way of illustration, really, is Zoo. The way the Zoo processing service works is it uses a path prefix to distinguish a context within the service. So it could be a username or it could be the name of a project, and so we can use that as a resource within Keycloak, against which we apply an authorization policy, in particular one that allows only this EOEPCA user. So that's what we're going to use this script to create within Keycloak. Bit of that. Okay, so we run the script. So we've got some questions that are needed to interface with the Keycloak API. Okay, so enter the client ID that needs protecting. Okay, so that's going to be this one, the one that we've just created. What's the username who's going to receive access? Okay, so the defaults are good for us here. The display name, so when this is configured within Keycloak, there's a display name. I guess it's designed to be something descriptive. In our case, we can just use the username. Resource type, it's possible to specify policies that are linked to the type of a resource. It's not relevant in this particular case, but each resource, when you add it, nevertheless has a type. We'll just stick with the default here. Okay, so now this is an important part of the permission, is which path within the service is this resource applied to. So what we're doing here is we're protecting this context for this user within the service. So I think, so this is the value we want. I think it's the default in the script anyway. Okay. So what we've done there in Keycloak is configure a number of things. If we quickly jump to Keycloak, we can see it. So if I refresh, we've now got this new client. And if we go to authorization, we can see we've got this resource that's been added. There is a permission that's been added, and the permission establishes a relationship between that resource and a policy. Okay, and so what ties it all together is, what is the policy? The policy says that the user must be a member of this particular group. Okay, and so to complete the picture, it's created a group, and the only member of that group is our EOEPCA user. So having done that, we will create the ingress that links to the policy. If we take a quick look, we can see how this ties together. So under processing, so generated ingress. So this is the ingress that's been generated. And so in this particular case, we've got the API 6 route as before, but it's got some additional plugins, and those plugins are interfacing with the Keycloak instance to enforce both authentication and authorization. And that is the thing. And importantly, the client that is used for that is the OAPIP engine client, against which these policies have been defined. So if we apply that here, okay, and then we can confirm the protection by running this script. Username, yeah, that's all good. Okay, so what's happened here? So it's done 3 calls. Okay, I might have gone quite slightly early on that because we're getting TLS connect errors. So 1 second, we can just check that. Orders. Okay, so we have an order. So just checking that everything is in place. Okay, maybe we just try again. Okay, so now we've made 3 calls. The first one without a token, and we're getting authorization required. Then 2 other requests to different endpoints within the API to list the processes for which we're getting an answer back with the token, and also to list the jobs. Of course, that we haven't run any jobs, so the answer is 0. But those requests are succeeding. Okay, so that's validated the protection that we've applied, and now we can also run the more typical validation scripts, which is just checking again that all of the usual pods, services, endpoints are behaving as expected. Okay, so as the final piece in this, we're going to interface as that user with the API to actually run some processing. So I'm going to just step through these one by one. So first of all, it wants us to ensure that we're using bash directly in order that this sourcing this script will grab us a token, an access token, and hold it in an environment variable. Basically what that's all about. So okay, so we've got an access token. The access token is quite short-lived, so if we're a bit slow about following the subsequent steps, you may need to repeat this. Okay, so first things first, we can interface with the API to list the processes. Again, we can type the output. Okay, so there's just a built-in default process there currently. What we can do, so we have this process that we call, it's an application package we call convert. It's just effectively a dummy or a hello world example of an application package. It's defined by this common workflow language file, as is for all OGC application packages. And we can quickly take a very quick look at that. So fundamentally what's in here is there is a single container that is referenced by this workflow, and it's this Docker image here, just taking which is the single step within this. And what this will do is it takes a URL of an image and it will just resize that image. So like I said, it's very much a hello world application package, but it's designed to run quickly. Okay, so we can copy that and we can, so that's deployed that application package. So if we were to now move on, we can, there's an endpoint that describes what you've just deployed. Okay, So these are the details for the application that we've now deployed. So that becomes available to us as something that we can execute. So now we make a post request to the endpoint for that application. And the inputs for this describe what we want to do as an operation. So we want to resize this image, resize it 50%. Okay, so we've got back a job ID. At this point, it's interesting to jump to the cluster. And what we'll notice is there's a new namespace. Each job within the processing service creates a namespace. So we can sit and watch that, and we should see transiently the pods that execute the workflow. If we jump back to the dock, we can also poll the status of that. So if we copy that and paste that, we get a status for this job. So it's currently running. Jump here again. Okay, so now we can see that the job is starting. Takes I guess a minute or so. We can, guess you can monitor it once it's properly running. Okay, so that's the job. So you can see the progress. You can see the standard out of the job execution. Very useful if you're debugging it in particular. Okay, we can see it's staging out now. Different pods come and go. So staging out is where it's got the results and it's pushing the results to the object storage. Eventually this will get cleaned up and the namespace will disappear. If we jump back here, we can repeat this command. Still running. I guess if we keep an eye on the namespace, it should eventually complete. Okay, we can see terminating now, so perhaps if we check the status, our token may have expired at this point. Okay, so we get authorization required, and the reason for that is because the token we had in the environment is short-lived, so we can just repeat that call. That refreshes the token, and then we can go like this. Okay, so now the status is returning as successful, and as per the API processes interface, it gives us various links to various aspects. So for example, we've got links to the logs of the different steps of the execution. So we've got the main log of the workflow, the convert log, but we also have a log for the stage out. And then we've got the URL also of the results to actually get access to the assets themselves. So jumping back to the guide, so we've checked the execution status. Now we can check the results of the execution. Okay, so what this gives us is a collection, a stack collection, which is providing asset links in particular to the outcome. So we've got the catalog JSON, for example, and that links into the assets themselves. So from the results that we get back, we can see these S3 URLs, and we can check the Minio object storage to see those assets there. So just very quickly, we can use S3 command, and we can connect with the Minio service, and we can see those assets are included there. So just to wrap up, if you'd like more information, then there's various resources. So we have our web portal at EOEPCA.org. All of our work is on GitHub. So we have a EOEPCA GitHub organization. And I showed you earlier the read the docs for the project. So you can access all of our documentation there, including, of course, the deployment guide. Okay, thank you very much.